Hello, everyone. This is Elisa Baum. I'm Grid Gain Systems Director of Product Marketing. We'll begin in just a moment. First, I need to conduct a little bit of housekeeping. Could you please raise your hand using the hand icon on the GoToWebinar control panel to let me know if you can hear me okay? So let's see. You guys can hear me? I see hands. That's awesome. Next, during this presentation, you will be on mute, but should you have any questions at all for the presenter, please go ahead and enter them in the questions field in the GoToWebinar control panel. And at the end of the presentation, we'll take time to answer as many questions as we can. I also wanted to let everyone know that I will send a link to both the recording and the slides probably within 48 hours, sometimes a little bit sooner, just depends on how long it takes to process. So if you need to drop off unexpectedly, don't worry, I will send you a link to the recording as well as the slides. So with that said, I'd like to present to you today's speaker, Dennis Magda. He is Grid Gain Systems Director of Product Management, and he's also an Apache Ignite, the Apache Ignite PMC Chair. With that said, Dennis, I'll turn the floor over to you to present Scale Out and Conquer, Architectural Decisions Behind Distributed In-Memory Systems. Go ahead, Dennis.
Hello, Lisa. Hello, everyone. Thanks for the introductions, and thanks, folks, for joining this talk today. And this conversation is basically is our continuation of the in-memory computing essentials we presented a couple of weeks ago or a month ago. And today I want to go even deeper. I want you to show how distributed systems are designed internally. And basically, if you know this information, you can benefit from this. Because as this title of this talk states, scale out and conquer. And many distributed systems, including distributed databases, data grids, or other computational platforms, they just state that just take us, deploy us in your production, and you will get scalability and availability out of the box. But in reality, if you really want to scale out and conquer, you need to know more about a system, distributed system, that becomes a backbone of your next generation architecture. And today, basically, if to take a look at the agenda, we are going to review three main things that you can find in any distributed system, or almost in any distributed system in the market. I'm going to refer to Apache Ignite as an example of a distributed system and database. But anyway, many of the things that we are going to talk over today are applied to other products. It can be such as Redis, such as Hazelcast, VolDB, MemScale. The idea behind is the same, but the implementation details might vary. But anyway, so what we are going to look into. First, I want to spend more time discussing partitioning. And I'm not going to tell you how the data is being partitioned, how a cluster node decides where the data have to be stored, and how it will be processed. Today, I want to look at the partitioning topic from the angle of its pitfalls, from the pitfalls of event distribution. Because whenever we talk about partitioning and sharding, a lot of people just say that, oh, okay, you just take my product because you will get even distribution out of the box. In reality, it's not true. And not only because it's difficult to support even distribution of data between your cluster nodes, but simply because it's not reasonable because of some performance and scalability needs. And I'm going to explain you why. Next, affinity collocation. That's actually a golden component or a foundation of every distributed data grid or database that technically allows you to collocate data on your cluster nodes and execute SQL queries or other queries much more efficiently. And this is basically how you can make SQL database scalable and not losing any performance and gaining more benefits. And today, when we are going to talk about the affinity collocations, I'm going to show you on numbers. We are going to review some of the standard and basic operations that are supported by distributed systems. And we just can make simple calculations, seeing what would be our benefits if we, let's say, execute operation 1 over the collocated data, and what we can lose if we execute the same operation over the non-collocated data. Just something that I would like you to keep in mind when you're switching to a distributed system. And finally, topic. Probably it's the most low-level topic. It's about how the multi-threading concept and different approaches are used and implemented in distributed systems. Because we all know as application developers, we use multiple threads, different concurrency techniques, approaches. We do use different workers, waiting queues, and so on and so forth. And in reality, distributed systems also go for these techniques. And if you know specifically how a distributed system applies this approach or that approach, you also can tune, you can tweak in configuration for your specific use case so that you can get the maximum benefits possible. Okay, so let's move on and let's start with the partitioning. So partitioning, pitfalls of event distribution. As a reminder, so let's figure out how simple put operation is processed in distributed systems like data grids. And under data grids, here is you can, or caches like the Redis or Memcached or Hazelcast or Apache Ignite. Basically, whenever you want to put a new key into the cluster, you need to, your application needs to find out where this request should go on node 1 or node 2. And basically, this can be easily calculated on your application side. To calculate the destination node, we need to take the key. We need to calculate a partition number this key belongs to, and then your application will know where this partition is located, and this key with its value will be sent over to the destination node. It's pretty simple. And let's assume that for this specific key and value, Affinity function determines that the key is located on partition 2, which is highlighted, right? And this partition 2 is located on node 1. And technically, all this mapping from key to partition and to a primary or backup node is supported by Affinity functions. Affinity function is, as you know, guys, is an essential component of distributed systems, simply because it can fulfill this standard and essential operation of taking a key and finding out where what is the primary node and what is the backup node for this key. Next, and because also Affinity function, in addition to this task, Affinity function also takes care of partitions distribution. If you take a look at this diagram, here is we see that our sample cluster has only 11 partitions, and all these 11 partitions are distributed across 2 nodes evenly, right? So what this gives us to our applications, it means that basically you can use, if to assume that your application can run under 100 TPS, it means that you can split this TPS equally between your 2 cluster nodes. Also, this means that, for instance, you're going to have much more queries that are running in parallel, and some of the queries will go to partition 2, some of the queries will want to get data stored in partition 11, and this is how the data will be distributed, and the workload will be distributed. And this is how your overall TPS workload will be distributed across these 3 server nodes. However, let's imagine what happens next if we want to scale out our cluster. Okay, so we decided to add a 3rd node. And then our Affinity function, because we supposed that this Affinity function distributes the data evenly, it will reshuffle some of the partitions. Some of the partitions that previously belonged to node 1 and to 2 will be moved to the new node. And the same happened to partition 2 that presently stores key value of this sample on the diagram. And also, the good thing about this distribution is that now the overall workload is distributed across 3 nodes of your cluster, meaning that every node will do a third of the job of the tasks coded in your applications. And this is good, right? So here, as you can see that now, most of your nodes, most of the CPUs on your nodes are stale, you do not use them, and it's a good chance for you to write, to advance, to make your application more sophisticated, or to put more workloads to your cluster. This is actually how the main benefit, right, of distributed systems. Just distribute your data, and if you distribute your data, you also can automatically distribute your computations because the data is located across many nodes you have. However, on this diagram before, we used so-called naive affinity functions, naive function, meaning that there is some algorithm that decides that every cluster node in the cluster has to store an equal amount of data, equal amount of partitions. But what's wrong with this approach? Let's try to find out. Let's go back to our initial case where we had 2 cluster nodes and 11 partitions distributed among them. So, but then when we add the 3rd node, this naive function, affinity function, will move 4 partitions to node 3, which is totally fine, right? So this is what is expected. But also this naive function might move, might reshuffle partitions between node 1 and node 2, meaning that some of the partitions that were stored on node 2 can be moved to node 1 and vice versa. And this is something that we don't want to happen in production. In production, some of the companies, some of the products, for instance, such as Ignite, they provide so-called fair affinity function that spends significant time trying to calculate even distribution when your topology size changes, but it takes time. It takes time to achieve this even distribution of your cluster. And in most production scenarios, distributed systems use a different version of affinity functions. Some of the products use consistent hashing function, and other products, for instance, such as Apache Ignite, rely on rendezvous affinity function. Those affinity functions are productized, meaning that they found a trade-off between even distribution and performance. And that trade-off was proven and satisfactory for, I don't know, for the most of the deployments of these distributed systems. So you can read more about consistent hashing. And today, let me quickly walk through the rendezvous hashing that is used in Apache Ignite. The rendezvous affinity function decides who will be a primary and backup node for a specific partition by comparing weights. And those weights are assigned using special algorithms of this rendezvous function. If to take a look at this slide, first let's imagine that we have some partition and we want to assign this partition to node 1. And presently in our cluster we have only node 1. So this node will get the maximum weight possible at that moment, and this partition will be located on this node. But then over the time we are adding second node. And when the rendezvous function starts its calculations, it will find out that, no, there is no need to, so I want to assign this weight to node 2 using that predefined algorithm. And since that weight for this partition, for partition A, is less than 100, that partition will stay on node 1. However, over the time, we can expand our cluster further and add the third node. And the rendezvous affinity function can change its initial decision and decide, okay, now I will assign weight 150 to node 3 for this partition, and that partition will be migrated to that node. And the same will happen, the same calculations will be happen for all the partitions we have in our cluster. And the idea of the rendezvous affinity function is that it will try assign weights to partitions and nodes in such a way that it will try to achieve even distribution of the partitions, but not sacrificing the performance. And now if we go back and look at the same scenario when we had 2 clustered nodes and 11 partitions stored on their side, and now we're expanding our cluster to 3 nodes. Rendezvous affinity function will do this that weights calculation, and we'll decide that node 3 will get more weight for partition 0, 5, 4, and 10, and those partitions will be migrated to that node. But at the same time, as you see on this picture, there was no any partitions reshuffling between node 1 and node 2, which is what we wanted to achieve for our production environments. And technically, this allowed us to minimize network noise, data movement across the network, and the render affinity function tried to do all its best to achieve the even distribution. In fact, with this distribution, it was not that even. So in reality, you can come up with the distribution of the partitions you can see on this slide, which will result that some of the nodes will do more work than the others. But that's one of the possible use cases. So, and the partition distributions, how the partitions will be distributed, totally depends on the number of partitions you have configured and on the cluster side. So it all depends. So, and here is the main point here is that productized affinity functions, they try all their best to distribute all the partitions evenly. But also at the same time, they do not forget about the performance. And also their goal is to avoid data and partitions reshuffling between the nodes that were in the cluster before you expanded it. And this is why, and this is only why you can see in reality that after you add a third node to your cluster, you can get a little bit, you can get not that even distribution of data. But this can change over the time when you keep expanding your cluster. So just keep this in mind and never be taken in by different slogans and statements that distributed systems always distribute data evenly. So they try all their best, and there are some affinity functions that do this, and even in Ignite we have that fair affinity function. But usually customers prefer performance. They also want to see not only that only even distribution, but they also want to get the performance when and to avoid data reshuffling when the cluster scales out. So that was about affinity functions. Let's move on to the second topic. Let's talk about the affinity collocation, looking at some of the basic operations and comparing operations number depending on whether our data is collocated or not. And here is, let's start with the simple use case. Let's assume that we have some account. It can be our bank account. So our bank account will have its unique identifier, and it will be opened in some city. So that can be one of our imaginary class. And then let's assume the data is not collocated, meaning that, for instance, if we have accounts opened in Moscow, those accounts can be distributed across all the nodes you have in your cluster. And in this example on this slide, we are trying to do a simple operation. I want to move money from account 1 to account 2, and I know that those accounts were opened in Moscow. But since there is no any affinity collocation between accounts and the cities they were opened in, both account 1 and account 2 can be stored on different cluster nodes. And let's assume that account 1 is stored in partition 6 on node 1, and account 2 is stored in partition 4 on node 2. And whenever I want to do this update transactional, I'm going to use Ignite transactions that basically work this way. First, here is we see that the transaction involves 2 cluster nodes. So my application is going to send requests to both nodes. Next, most likely we are going to have a backup copy of all our data in the cluster, right? Especially if you want to move money over it. So this is why all these 2 requests that would come to our primary nodes, the primary nodes will also ensure that the data will be updated on the backup nodes. So this is how we get 2 extra requests from primary to backups. But also we must not forget that Ignite uses two-phase commit to ensure data consistency cluster-wide. And all this means that technically your application is going to exchange two sets of requests with primary and backup nodes. The first set of requests goes for prepare phase, and the second goes for the commit phase of the protocol. And finally, that's not all. Also, backup and primary nodes have to acknowledge recipients, the recipients of the requests that are coming from your application. And this gives us in total 16 operations. So just if you want to move data, move money from one account opened in Moscow to another account, it can take us 16 operations. Just imagine this. And that's actually, this can happen. And if that transaction was executed on a single machine, we wouldn't care about that, right? Because who cares? It just executed locally in 6 operations, local operations are nothing. But these are network operations. All these 16 operations involve network round trips. And depending on the throughput and latency of your network, your performance of your transaction can vary dramatically. What can we do about this? For instance, in this specific use case, we could technically come across a good solution that would help us to optimize and speed up our transactions, especially when we want to move transactions between accounts opened in the same city. So here is we can use the Affinity collocation approach. Okay, let me use this. I can use the same account, and I just can say that, okay, so every my account will be collocated with the city it was opened in. And I'm just going to use this Affinity map annotation. That's actually the annotation in Ignite. And in Ignite also provides you in other ways how to define which field is collocated. Other products such as Redis and Hazelcast and WorldDB, they also have special notations on how to define affinity fields or affinity columns in your data model. So basically, it will work the same for these products. So now we collocated the data, right? So and let's see what happens with the same transaction. And now we know that all the data, that is all the accounts that were opened in Moscow, they will be collocated on the same node because they will be stored in the same partition. And this is what's basically shown on this cluster node. And now, as you see, our application, when our application wants to move data from one Moscow account to another, it's going to interact with a single cluster node, which is great because it's going to send one network request to the primary node. That primary node needs to update only one backup copy of the data because both transactions will be stored on the same backup too. And finally, here is we can simplify the two-phase commit. Whenever Ignite sees that there is only that all the updates, that all the whole transactional updates spans through single primary and backup node, it will simplify. It will be turned into the one-phase commit protocol. And one-phase commit protocol simply just commits data to the backup node. Whenever you send a phase message, actually that phase message will be turned into the commit message right away. So once the backup primary node receives this update, it will be sent the update to the backup node, and it will be updated then on the primary node, and both nodes will acknowledge the request that came from your applications. And in total, we would reduce the overall number of operations from 16 to 4. And that was done only because our data was collocated initially. And basically what it means for the distributed systems, it means that you can get 4 times more performance increase for these specific operations. Yes, in reality, so you're going to move data, if to take this example, and if you just store bank accounts and you're moving money from different accounts opened in your system, there will be a lot of situations when you need to move data, let's say, move money from Moscow to New York or from Moscow to London. And in that situation, your distributed system will use a two-phase commit protocol, and it will basically involve 60 network operations to complete the transfer. But also in practice, there are a lot of operations and transfers that happen locally, like on a territory of specific city, like Moscow, like London, and like New York. And if you know that the data is collocated in advance, and all the accounts stored close to their cities, you can get that performance optimizations when two-phase commit protocol is turned into the one-phase commit protocol, and you can execute your transactions much faster. Okay, that was the benefits of using Affinity collocations for transactions whenever it's possible. Next, let's take a look at SQL. So a month ago, when I was presenting in Memory Computing Essentials, and when we were discussing Affinity collocation concept, I showed its main benefits for distributed joins, because distributed joins are possible in distributed systems, in distributed databases. Many vendors, many legacy vendors, and many relational database vendors, before they stated that it's not possible to execute distributed joins efficiently over the cluster nodes. But now take a look at Google Spanner or take a look at Ignite. Both products disprove that it's not possible. You just need to collocate your data in advance properly, and then you can execute distributed joins. So for the distributed joins situation, the Affinity collocation is almost a must. But also the Affinity collocation can be useful for simple queries, like the one shown on this slide. Here is we're just trying to execute some straightforward. I just want to get, I don't know, let's say some accounts that are stored in Moscow again, and that's probably one of the simplest SQL queries possible you can run over distributed SQL database. Again, and here is, let's assume that the data is not collocated. So we have not collocated our data, meaning that all the accounts operating in Moscow will be spread out across all the cluster nodes you have. And what will we get in advance? Let's see the numbers. So basically, if we're using the classical the relational database, all the data will be stored on a single machine, and whenever we would run that query, it will do the full scan using all the resources of your machine. I mean that, and this is shown to the left. However, now all the data is distributed across 3 machines, and basically the overall latency will be reduced 3 times, because now you can use resources of 3 machines to complete this query, and it will be completed faster. And also you get 3x throughput grow, because now you can run much more, technically you can run much more queries in parallel, not worrying about contention and the fact that your CPUs will be overused simply because there are too many full scans are running in parallel. But those are full scans, and this is probably one of the simplest approaches you can take if you use SQL queries. But in reality, full scans are applicable and reasonable for small data sets. But whenever you want to iterate or request data working through a large data set, you start thinking about indexes, right? And when we think about indexes in relation to a classical relational database, we can imagine a single tree. And that just tree structure assigns and maintains indexes, your index data, and then you just need to iterate over this index data to find required values and to complete your query as fast as possible. But what happens if you define indexes in distributed system, like let's say like Apache Ignite, like MemSQL, or like Google Spanner? Basically, you're going to have a forest of trees. So every cluster node will store its it will store and maintain its copy of a tree that corresponds to the data that is stored on this cluster node. And now let's try to calculate, is there any benefit for the index search if we took that single tree and split it into a forest of trees? let's assume that there are 1 million records, 1 million accounts stored in our database. And technically, if all those million accounts were stored in a relational database, single node relational database, it would take us around 20 operations to complete an index search. But at the same time, if we just decided to distribute this data and define index, and that query will be executed over 3 nodes, it would take us just 18 operations to complete the query. Not that big difference, right? So in reality, when you do that, such an index search or the non-collocated data, you are going to have almost the same latency, so the query will be executed approximately at the same time. And also you're going to have probably the same throughput, because the index search is really fast. Yeah, it's just flashing, it just happens, it's quick. And there are not that many benefits for the distributed scenario. But how can we reduce the latency, or how can we increase the throughput if we decided to use indexes and we want to store our data in a distributed database? It's pretty easy. Again, we need to collocate our data. And if we now collocate all the accounts and we'll store them on the same nodes where they were opened, then this query will be sent to a single node. So here's, again, we assume that Moscow account is stored on node 1. All the Moscow accounts are stored on node 1 in partition 6. Then this is why when you will try to execute this simplest query possible, it will be sent directed to this node 1. What's good about this? It means that that node will take the same time for that node to execute this query. So you will get the same latency in compared to a relational database, a single node relational database. But you get much more throughput, because now you can execute the same queries that will get the same data, but for the accounts opened in New York or London. And if all the accounts opened in New York and London are stored on the other nodes, then you can use resources of the other nodes in parallel. And this is actually how the affinity collocation can be used, how you can benefit from the affinity collocation for your index searches in distributed system, such as Apache Ignite, such as Google Spanner, or such as MemSQL. So just keep this in mind. And final topic for today's conversation, let's go even deeper and see how distributed systems use different multi-threading and concurrency approaches and techniques in practice. So what you should know and what you should be aware of. So first, whenever your application sends a query, a task, a calculation, or any other sort of request to your cluster, to your distributed cluster, all those requests will be processed internally by your cluster node using special workers. So that's a pool of worker threads that can be executed in parallel on an individual CPU core available on your physical or virtual machine. So it's a pretty simple approach, right? So just there are millions or thousands of different queries that are coming to this specific cluster node, and that cluster node distributes the workload between the internal workers that can be run in parallel on your CPUs. But as many other applications, those workers got stuck fighting for different resources. And on this diagram, we see that in circles, we define different data. The data that is stored on this cluster node and the data that might be needed for these workers to complete and acknowledge your request, task, or query. And here, as we see, a classical theme that is familiar to every developer that created or developed any distributed or multi-threaded application. Here is we have 3 workers that are fighting for a single resource. It will mean that might be some data that is stored on this node. And if you want to be sure that every worker accesses this data exclusively, the rest of the workers will wait. they will be halted and they will wait while the first worker completes its task. And also, to make things worse, all your queries, all your requests that are coming from your application to a cluster node, they are first read from the cable, from the networking cable using NIO threads. That's true for Java. Other distributed databases like MemSQL or VolDB that are written in C and C++ are going to use similar approaches. And basically, and here is in Ignite, we use NIO threads. Ignite takes reads data from your network, your request from network, and puts this request into a special working queue. This working queue is shown here as a combination of 3 orange squares. And here is we see another bottlenecks, right? So first, the NIO threads are fighting for the tail of this queue, and the worker threads will contend on the head of this queue. So meaning now in this scenario in your distributed system, you can get 3 bottlenecks. And depending on the workload of your application generated by your applications, you can see how the data and the performance goes up or goes down depending on the type of query you run or on the type of data your workers need to work with. And yes, and actually that's a pretty significant bottleneck. And technically, what can we do about that? Specifically, if we know that workers have to work with, can fight for data that is stored on a local node, we can distribute this data somehow. I mean, then we can distribute the workers in such a way that they will be responsible for a specific subset of the data. So what we know about the data distribution on a local cluster node? We know that all the data is stored in partitions. And we can gain from this knowledge, we can tap into this knowledge, saying that, okay, I have, let's say, 4 workers, and I have, let's say, many partitions. And I want the first worker to be responsible for partition 1 and through partition 5. Worker 2 will be responsible and will process all the queries that are coming for data stored in partition 5 through partition 10, and so on and so forth. So now, whenever you try to execute your query computation, and whenever we see that computation or query wants to get data that is stored in a specific partition, the internals of your cluster node are going to work with a special worker, so that to remove that bottleneck that could happen when workers fight for a single for concrete data. So how can we benefit from the knowledge of partitions? We can remove the rest of the bottlenecks. We can say that the NIO threads, some of the NIO threads, specific NIO threads will be responsible for specific partitions, meaning that if a request, like key value operation or transaction that moves data from one account to another, comes to this cluster node, and all the data is located on partition 1, then the NIO thread that is responsible for this partition 1 will process this network process. It will put this request in a special working queue that is created for the first worker, and that worker is going to take jobs out of that. So basically, and this is how you can remove these contentions. And this is how many distributed systems also tackle these contentions and provide you this so-called thread per partition approach parameters, when your queries and when your local workers are distributed among the partitions that are stored on your cluster node. However, you also should keep in mind that that's not a silver bullet. That's not a kind of a magic functionality that will remove and solve all the bottlenecks of your system. Meaning that you also need to judge on when you're deciding to switch from the previous approach, when the data and workloads are distributed between the workers randomly, and sometimes you also need to consider this use case. For instance, if your data is collocated, it can happen then some of the partitions will be fatter, bigger than the others. Here's on this picture, we see that, for instance, there are too many accounts opened in Moscow, or it can be New York or London, big metropolitan cities. But smaller cities like St. Petersburg or such as San Francisco, they can have less accounts opened, meaning that there will be less data stored in specific partitions. And it will come to the fact that whenever you use that thread per partition approach, you can get to a situation when there are many queries, there are many transactions or queries that work with the data opened in Moscow region or New York region. You can have a situation when almost only one worker thread is being used on your cluster node. And you can see that and from visually you will detect this as you'll see that only just small subset of your CPUs are used, while the rest of the CPUs stay stalled. And basically here there are different techniques. So if you know that the data, how you can tackle this, how you can avoid this. So first, probably you can just split such big cities on districts, meaning that you want to collocate data not by city or by district. Or for instance, if it's not possible, just do not use thread per partition technique for these specific data sets stored in your distributed system. Just use the general approach when all the queries and when all the computations that come to your data are randomly distributed across all the workers that are running on your cluster machine. So again, it's a good point to know and a good point to consider whenever you design your applications for distributed systems. There are different trade-offs, there are different techniques, but if you really want to benefit from a distributed system, you need to be sure that it's tuned and your applications are developed and adapted properly so that you can gain knowledge from all the details I shared with you today. So the upshot, what we learned from today's presentation. First, the partitioning, this holy grail of distributed system, partitioning or sharding. It's not whenever you work with a distributed system, the partitioning algorithms do not care, they care not only about even distribution, they also care about the performance, and they also try to avoid data movement and or partitions redistribution between cluster nodes that were in your topology before you decided to scale it out. So don't be surprised if you see that some of the distributed systems when you see that distributed systems distribute data not evenly. So this can happen. So and usually there are different techniques. If you somehow find out that the distribution is too sparse or something goes wrong, then you just need to check partitioning parameters. Probably a number of nodes in your cluster goes beyond number of partitions, and you need to increase the number of partitions to rebalance and to fix the distribution of your systems. So just keep this in mind. Affinity collocation. So that's a golden concept, and that's probably one of the main foundations of distributed systems. In the previous conversations, we saw and learned how it's useful and required for distributed joins, for MapReduce-like computations. And today, I hope that you learned that even simple operations like simple transactions or simple SQL queries can also benefit from affinity collocation concept. All this, the affinity collocation concept benefits mean that you need to adapt your business data model for a distributed system. Yes, some of the products, many products, distributed products, say that you just can take us and deploy and run in production almost without any changes. But in the reality, you need, if you can, and for some of the products it might be true, but the performance might be not appropriate. But if you want really gain all the benefits of distributed system, you need to consider affinity collocation, meaning that you need to revisit your model, and most probably you need to adapt your model to make your applications lightning fast. And finally, thread per partition technique that is common for many distributed systems. It's really great. It's really useful because it helps us to utilize local resources of your individual cluster nodes as efficient as possible. But also, you can come across scenarios or operations that can work worth with this thread per partition approach. And how to tackle them? Try to revisit your data modeling, like I shown on the previous slide. When we had a big partition with all the accounts in Moscow, you can try to split it on districts. You can collocate by districts, or you can use other techniques, more advanced techniques that are available, or probably a thread per partition approach is not just good for that specific query, for that specific data set, and you just can switch to the classic approach when the data and queries that are coming to your cluster nodes are distributed randomly across all the workers that are running on that machine. So, and resources. Today we talked about the low-level features. But if any of you haven't visited the in-memory computing essentials that were presented a month ago, I would and wanted to learn more about the basics of distributed systems such as Apache Ignite, I would recommend you to watch the recording of these two part series. And also, if you want to read more about Affinity collocation, start with this documentation available on Apache Ignite. And also, then you can just walk through many other topics and materials prepared around this concept. So, and now we have time for questions and answers.
Hello, Dennis. Can you hear me okay?
Oh, yeah.
Okay, great. And I apologize if I sneeze. I'm thinking I'm coming down with the dreaded flu. Good thing you guys are not near me. This is virtual. Okay, so this was asked early in the webinar, and I apologize if you addressed it, but is GridGain multi-core and multi-threaded?
Yes. GridGain, Ignite, and also other many distributed databases, they can scale both horizontally and vertically.
Okay, next question. Does Ignite provide Btrees, and are they used for sorting?
Yes, so presently, starting Apache Ignite 2.x, B+3 became an essential part of the overall memory architecture. So all the primary indexes and all the secondary indexes you define in Ignite are maintained and sorted by B+3 data structure. And B+3 are used not only for SQL queries in Apache Ignite. Even when you run a simple cache operation, such as cache get for some key, this key, we are going, this key, all the key values are stored in the B+3, and this request will go through the B+3 data structure.
Okay, the next question. How do you configure the thread per partition option in Ignite?
Oh, I don't remember by heart, but so you can send us a message on the dev list and we will direct you to that configuration parameter. Sorry, that's my bad that I forgot to include it in the reference slide I showed before, but just send us a message to the dev list.
Okay. Next question. The web console generates the initial model based on an imported schema. Why isn't Affinity collocated configured in the model out of the box?
Yeah, it's a lack of that thing, and I do know that the community we have a ticket. We have a ticket to support this. Probably over the time it will be prioritized and implemented by one of our contributors and commuters. But that's a good point. Unfortunately, that's not because we cannot support it. That's because the community were interested to implement other tasks that we have for Ignite.
Okay. Next question. A generic question. Would you be able to comment on Apache Ignite's product vision in the age of the cloud? So, for example, AWS, managed services, Azure, etc., and general industry of evolution towards going serverless, like AWS Lambda.
So actually, speaking about our community vision, so we are on the track and we have totally support their cloud-based deployments. So as you know, I might get not your question correctly, but from what I hear, Ignite, you can deploy Ignite whenever you can. You can deploy it on AWS, and we provide special components for AWS so that all your cluster nodes can auto-discover each other there. And so this just works. And technically, I know that there are a number of Apache Ignite users significantly grow. Apache Ignite users who use cloud deployments has significantly grown since the time we supported essential things needed for cloud deployments. So, and I think that this trend will evolve in that direction. We will see that more and more companies are going to deploy their applications and their clusters in the cloud, even financial companies such as banks, because they see the benefits of the cloud systems. And I hope that someday almost everything will be deployed in the cloud.
Okay, and one question, I think there's a typo in this, so I'm gonna read it to you with what I think is not the typo. What is the difference between Professional Edition and Enterprise Edition? Or they say PE and EE.
Yeah, I guess that question is about GridGain. So Professional Edition, so GridGain is an enterprise level provider of Apache Ignite. And Professional Edition is the same as any other Apache Ignite distribution. The only difference is that GridGain can release hard fixes and improvements that will be available to Apache Ignite a little bit later. So you as a GridGain Professional Edition user can get fixes and features that will go to Ignite quicker. But as for the Enterprise Edition provides additional functionality on top of Apache Ignite and on top of, let's say, Professional Edition, such as data center replication, advanced security and audit, then additional management and monitoring capabilities. Those are the features that are not available to Apache Ignite users.
Okay, let's see, there's one more question. I think we have time for a couple more, so if you have any more for Dennis, you want to try to stump him, go ahead, now's your chance. So the next question is, for a developer new to implementing distributed databases on Apache Ignite, what is your advice for learning without spending a lot of time in trial and error and observation?
So it's a good and broad question. It depends. If you want to start, if you want to learn, if you want to use Ignite as a distributed database, just start with our documentation, because our community tries hard to make the documentation as clear and as vivid as possible. So we prepared good articles and good technical documentation about Ignite persistence, distributed persistence. Also, we prepared a completely new, if you're going to use Ignite SQL queries, we prepared a completely new and redesigned SQL documentation domain, where we aggregated all the knowledge about our SQL capabilities. And that SQL domain and that SQL documentation will look familiar to you if you are an experienced relational database user. So just go there, see what is supported, how to use our SQL queries, what kind of drivers we support, and so on and so forth. And as for the memory configuration and Ignite native persistence, also just start with our technical documentation. If something looks confusing or not clear for you, just don't hesitate to send a message to us on the user or dev list, because we take all such inquiries seriously and we try to tweak our documentation as fast as possible. And also we will immediately provide you a feedback and answer on your question.
Okay.
And finally, also forgot to mention this, there is a good book written about Apache Ignite. It's written by one of our contributors and enthusiasts. It's just says, it just explains Apache Ignite in details and shows the main components that are supported there. You also can consider it as a good starting point in your learning curve. All the references to the technical documentations and to the book can be found under the resources section on the main Apache Ignite site.
Okay, great. Next question. Could you please elaborate on the previous question about the cloud and specifically how Ignite will play in the future world of serverless?
I guess that I'm not in this, actually I haven't, serverless, I need to investigate this because I heard this word, I read some articles, but technically I was not interested in this topic and probably not the right person to elaborate on this. So I would suggest you to also send a message to our dev list raising this question. And I guess we have kind of community members who are in this topic and will be able to explain on our vision. Probably you're just saying about the thing that I named differently, but I don't know how to answer this question right now.
Okay, and I think we have time for one more question. And that is, apologize, I got out of order here a little bit. Can native and memory cache configurations coexist in a cluster?
So you can use, right, so as far as I understand, the question is, can I have data that is stored in memory only and the data that is stored both in memory and on disk in Ignite native persistence? Yes, the answer is yes. It's up to your memory configuration. You can define special, we call them memory regions, and you can say that memory region 1 will store data in memory only, and you, let's say, give it 10 gigabytes of RAM. But also you might define another memory region that will occupy 20 gigs of RAM, and also all the data will be persisted on disk. That's possible, and technically you can see how to define this by going to our technical documentation. We have a sample, a code snippet for this situation there.
Okay, so that brings us to about the top of the hour, and I want to thank everyone for attending today's session. Please join us on January 31st. Akmal Chaudhry, who is our technical evangelist for Apache Ignite, will be presenting Ignite the Fire in your SQL app. So we encourage you to go ahead and register for that, and even if you can't attend live, we'll send you the link of the recording and the slides. So please go ahead and check that out on gridgain.com. So with that said, everyone, thank you again so much for your attendance today. And Dennis, thank you for another wonderful webinar, and we look forward to your future presentations.
Thanks a lot. Hope to see all of you the next time.